Good morning, Michael. How are you this fine morning?
Good morning, Matt.
You see, I'm really ready.
Even the cap is off.
The cap is off, the pen is shaken.
So what are we talking about today?
We're just going to have some fun.
Okay, fun is good.
So I want to start with back to basics. So if we have an independent variable x,
okay,
and we have some function which we can call a map, it's a rule, it has special properties, and we get y. And so the way we have been writing that is y is equal to f of x. So graphically, we can think we start with an independent variable and we get a dependent variable. And a lot of our previous discussions have been looking at the slope of f and the best linear approximation to the slope, giving us derivatives, and we went through all that wonderful analysis. I just want to change this a little bit. Supposing I give you y and I ask you, find me the x. So I want to go backwards. So now y is the independent variable and x depends on y. So it's the opposite. So we could call this g.
Okay.
And so x is equal to g of y.
So I think in our last video we had a few examples of that. So for instance, I think we had an example where this was something like a cubic function and this was the cube root.
Right. They're kind of opposites. And in fact, we can use composition of functions and we can say that x is equal to g of y, which is f of x. So that's
this x and this x, the same guy.
Same x. This x here, that x there, same x.
Okay.
Now, what we've done here, if you look at these two, we kind of flip the role of x and y. So let me give a real life example, which we'll look at later in more detail. But say I take y is equal to the sine of x. And we know what the sine looks like. I'm not going to draw it out. But now I'd like to have a different function that takes me backwards. So I'm going to say that y is going to be equal to the backwards version of this. And I'll put -1 to indicate that.
Okay.
What do you think of this notation for the backwards map, if you like? Because if I take the sine of each side, and this does backwards, we're going to get sine of y is equal to the sine of the inverse, the backwards one. And so what will we get when we do this?
Well, just like you had here, one function cancels the other function, so you're left with x.
That's exactly what we have. So if we look at the original function, y equals sine of x, now we've got the, if you like, the opposite relationship, x equals sine of y.
Okay.
So we flip y and x.
Sure. Because y and x are just numbers, so we can put them in either place, right?
But now we can take that and look at it geometrically.
Okay.
So I need to erase this. Well, now that we have a clean board, let's go to geometry.
Okay.
Because this is really, really important. So I'm going to start with, okay.
So your x and y.
I'm starting with x and y. Now I'm going to, for y is equal to a function of x, we can just pick any point. So we'll pick a point x and a generic point y for that particular choice of f. I'm going to put it on the graph. So I'm going to put it here. And for the conversation, I'll put an A here.
That's your point A. Okay.
That's my point A, and it has coordinates x, y.
Okay.
Now, we just talked about flipping y and x. So I want you to put the point B where these guys are flipped.
Okay, so I have to flip x and y. So x is about here. So I look at a similar point there, and y is about here, and that's going to become the x value. So I would think it's roughly here, and I'm going to call it b. And you want me to write
Exactly
b of
the
yx?
same coordinates, because I'm just flipping them. So whatever I pick for this pair,
So this is y and x.
terrific.
Okay, so they've just switched.
We
Okay,
just switched. Now, these 2 points, A and B, have a special relationship. And here it is. When I'm flipping these, this point here moves, A moves to B.
okay.
Where's the point that doesn't move? There's one choice of A that doesn't move when I go from A to B.
So there's a line from here to here. If I was exactly in the middle, this guy, it wouldn't move.
Yeah, so what point is that?
That's where x and y are equal.
So X comma X, so put that on.
Okay. X, comma, x.
Now,
Okay,
you said that this distance is equal to that distance. Now, why is that?
well, I could write down a mathematical formula, but I think the quick answer is if I flip this, I go to this.
Well, let's actually do the,
Oh, you're going to do the math? Okay.
we're going to do the math.
Okay, so the distance from here to here, okay, you use a Pythagorean rule.
Well, I'm going to actually do it like this. First of all,
I think,
here-
Matt,
wait,
you might
I got
need different names because this x and this x are different numbers.
Oh yeah,
This
that's
x and that's x, so maybe can I call this, maybe
let's
put a little hat on it or
let's
something.
put B's and A's in here and call this C. How's that? Do you want to do that? I'll put XC, XC. Or what?
Sure, xc.
Okay, and this will be XA and YA.
Well, this one's okay because these x's are the same x's and these y's are the same y's.
Okay, so I'll put a C here,
Okay.
and I'll
I'm
put
happy
a
with that.
C there, and we'll put a C here.
Okay,
And then we could write a song saying, "Oh, say, can you see?"
sure.
We'll, now, we want the line that goes through, starts at the origin and goes through C. It's going to be a little bit off, but yeah, you draw it. From the origin through C all the way through.
How's that?
Good. So we could put the line Y is equal to X.
So this is a line. Okay,
Now, we're going to do this. First of all, if we take the line that joins these 2 points, what's its slope and why?
well, this guy, slope is 1. Because here y is equal to 1 times x. Slope is 1. This is perpendicular, and we know to get a perpendicular slope, you take the negative reciprocal. So take 1, reciprocal is 1.
Yeah, except that
with a minus sign.
there's one
The slope
point
is
here
minus
that
1.
we're assuming that the person doing this remembers and understands and is able to prove why it's perpendicular minus 1 over m. So I don't want to assume that. We're going to actually prove it.
Okay.
And the reason is it's good geometry.
Oh, I think I can do it. Slopes are rise over. Well, you want the slope of this line, right?
Yeah, so first of all, yeah, okay, what's the slope of that line?
It's minus 1.
How'd you get that?
Well, because I can see that this went down. It went from this y value to x. So the distance change is y minus x. And the distance from here to here is x minus y. So it's the same number with the minus sign. So
Yes.
the slope, rise over run?
It's minus 1. So right away, without having to remember that, we have a
Fancy fun.
geometrical intuition.
Okay, there you go. Good.
Now, the next step. We're not assuming anything here other than basic straight lines. I want you to find that point of intersection. Can we do that? It's 2 lines. So we know the equation of this line.
Well, I can see it. See this line, it's halfway in between. So this has to be x
But you
plus y
still,
over 2.
I'm not assuming, I want to show the halfway part. You're making a leap.
I'm not making a leap. I think anyone can see that this distance here is the same as this distance here.
But that's by construction. I want to see the.
Okay, I can do okay, so you look at the length squared is the x values different squared, y values different squared. So here, xc minus x squared, xc minus y squared. This guy get the same thing, x minus xc squared plus y minus yc squared. So the distance squared are the same, so these distances are the same.
They are the same.
Categorical.
Another way to do it.
Yes. Okay.
Okay, this line is y is equal to x.
Okay.
And we need this line. Well, we do y minus y naught, so I guess we'll pick xc as y naught. So we have y minus y naught, which is xc, is equal to the slope times x minus xc. Now we're going to solve for xc in terms of y and x.
Okay.
So what does that equal to? Well, this minus xc, and we got another plus xc. When we move it over, we're going to get 2xc is equal to x plus y.
Right, because your x went over to the other side.
X went over to the other side, so now xc is just the average.
Yep.
Now, without doing all the algebra, since we have symmetry here, we can write what yc has to be, or just knowing we're sitting on the line that's where they're equal, we get this.
Okay.
So that's good. So now we know that this distance is equal to that distance, but geometrically, and you did it Pythagoras directly, but now we have an intuition here. So this line, y equals x, is like a mirror.
Right, because everything on this side is going to be reflected over the same distance and perpendicularly across this line, y equal x.
So now we have an operational way of taking a point here, and when we flip, we go over there.
Okay.
If we do the flipping in the right way, then we can go back to what we did with sine and sine to the minus 1.
Okay.
That means if this point is representing sine, this point would be representing sine to the minus 1. Now,
Okay.
thing is, there's very few functions for which you can do this because we have a closed form representation of the function. So we know how to draw sine, but not everybody knows how to draw the backwards version,
Right.
the sine inverse. Now, if we know what the sine is, and we know how to flip things like this, interchanging x and y, then we just have to do that point by point.
Okay.
We now also have to figure out how the slopes go from this point to this point, but we already kind of know what that's going to look like because we can do it for a simple straight line. So we know what the slope of the straight line is going through this point. Then we know what it will be for that point.
Okay.
And we can do that very straightforwardly. That means if we know what the function is like sine, say it's goobel, and we want goobel to the minus 1, we just point by point pick a point on goobel and then flip it to get goobel to the minus 1.
Okay.
And we also can draw a little piece of a line there indicating the slope there, and it might be different when we go over here. It will be different. It'll be, as you said, minus 1 over the slope.
Well, 1 over the slope.
1 over the slope in this direction.
Yeah.
So that means when we don't have an explicit form for the function like sine, hyperbolic sine, exponential, but goobel, we can construct goobel and its opposite by piecewise gluing these little line elements to get goobel to the minus 1.
Can I make a suggestion here? You've been talking about the sine function. I want to draw it for you. Can I draw the sine function?
Go
And then
ahead.
its mirror
Yeah.
image. So let's see if my pink pen works. So my sine function, we know the slope is 1 of sine at 0. So it's going to start off like this line. And then the sine function kind of goes like this. And then we're saying to get the, so this is sine of x. Now we show that for each point on this curve, we need to reflect it across this line, which I can do in my head. I pretend this is a mirror. So the mirror image would kind of go like this. That sort of looks like the mirror image.
Yeah.
And now what you're saying is if I had a little tangent line here, it gets reflected there.
Yes, and we know how to do this because we could just take any old line that goes through any old point, and we know what the slope of this line is point by point.
That's right.
Because it's easy to invert. Y is equal to mx.
Right, right. So if you have y is equal to mx, maybe we'll add a little b here. To invert this, I get y minus b times 1 over m is equal to x. So this slope becomes a 1 over m slope.
Right, and so that's the way, by taking these little, if you like, toothpick tangents and gluing them together, we can reconstruct the whole function. And that, you know what's nice about that? It means if we know the slope of something, we can glue the little pieces of slope to reconstruct the function.
That sounds like integration.
And you know what?
What?
That's differential equation.
Differential equations. Oh, absolutely.
So because in differential equations, you say, give me the slope, find the function. That's it.
That's what we're doing here. That's right. So if you have the slope at each point, you can slowly, like, I like your toothpick idea. You lay out a bunch of toothpicks with the appropriate slope, and it rebuilds the curve.
Fantastic.
Very nice.
Yeah.
Good discussion.
Yeah, I think this is great, and we'll follow it up because for many functions, we know how to build them easily because we have tables for signs, so the inverse is easy, but some functions are really messy. So we might have to solve an equation involving the derivatives only, and we can do it graphically in this way, and fantastic. We've covered a whole bunch of stuff that didn't appear before just by doing the geometry of straight lines.
Very nice. Well done, Matt. See you next time.
See you next time.